In the first half of this course, we focus on parallel database systems. In this module, we focus on techniques for distributed database system. So nowadays, most companies have multiple locations with their databases stored at multiple locations. This calls for distributed database system to support their day-to-day operation. A distributed database is a collection of local databases distributed over a computer network. Each of these database locations, in addition to support local application, support also global application that need to access data at multiple locations. From the network architecture, a distributed database system looks similar to a share-nothing parallel database system. The difference is that share-nothing systems do not have local application, in the sense that no one processing node in a share-nothing system is capable of executing an application by itself. Another obvious difference is that a share-nothing system resides at a single data center, whereas a distributed database system involves multiple locations, say New York City, Paris, and Shanghai. So when should we consider a distributed database system instead of a parallel database system at a data center? First, organizations often have multiple locations that need to enforce local policy regarding the use of local databases. A distributed database system makes this possible. We will discuss the difference between local database schema and global database schema later. Second, the performance of local application is excellent because the required databases are at the same location of this application, so no communications necessary. Parallel processing is also possible because the local application can run concurrently at different locations. Third, to achieve better reliability and availability, each database can be replicated at more than just one location. Losing a local database or a location even degrades the service of the overall performance of the distributed database system, but it does not render the service unavailable. And this is a big advantage over a centralized database system. Fourth, a distributed database system also makes incremental growth easier. It is very easy to add a new database server at a new location to an existing distributed database system. Fifth, we will discuss later that a distributed database design is often bottom-up design in the sense that local database systems already exist, and distributed database technology allows organizations to integrate these existing databases to facilitate sharing of local data through the global applications. Sixth, since organizations have mostly local applications that need to access only the local database, there is no need for the network communication. In a centralized database solution, the local application would need to access the database over a network. Distributed database systems do have some disadvantages. First, maintenance multiple database servers at different locations require more system administrators and incur a higher maintenance cost. Security is also more difficult to control since now data are transmitted and shared over the network, particularly over a public network. Another trade-off is that a distributed database system is more complex than a centralized solution. Although system availability is improved with data duplication in a distributed database system, This strategy makes database update more complex and more expensive in order to ensure the consistency among all the copies. Now, the synchronization of transactions on multiple sites is also more difficult than a centralized system. So let's first look at different distributed database management system architecture. A distributed database management system should hide the network from the global application. So all that complexity should be hidden from the application. The programmers of this application should not need to know about how to access the local database in their software. For instance, they would still use the standard SQL to access the distributed databases. They think that they are dealing with a centralized database system. This is achieved through a global conceptual schema that we will discuss in detail later. The user here refer to both end users and software developers. They are not aware of the database being distributed over a network. The application query a relation as in centralized database system, although the relation is actually fragmented and the fragments are stored as local databases at different locations over the network. The application are also unaware of data replication for better system reliability and system availability. As shown in this diagram here, a relation R actually consists of 4 fragments stored in 3 local database management systems at site A, site B, and site C. Information about the relation R is stored in the conceptual schema. The information about the fragments is stored in the fragmentation schema, and information about where to store the fragments is stored in the allocation schema. Data replication is supported in this scenario. For instance, the first fragment colored in green is stored at both site A and site B. In this example, the global application would query against the relation R without having to deal with the details of a distributed database residing at multiple locations. So the software development is more reliable and is much less expensive. Let's first review the standard architecture for a centralized database system. We can then explain how it can be extended for distributed database management systems. Centralized database management systems typically employ a 3-layer architecture as shown in this diagram here. At the bottom, the internal schema deals with how to map search key to record ID in order to retrieve the data items. It also supports various access methods such as tree-based or hash-based indexes. Now, these are the topics that we discussed in the second module. At the middle is the conceptual schema. This is the application view of the database, or the enterprise views of a database. In a relational DBMS, this layer enables the queries in the application to access the databases through table names and their column names. At the top, external schema is at the top layers. It supports a number of external views of the actual database, each for a different user group. Typically, applications do not need to use all the tables or all the columns of a table. The database administrator can use the create view statement in SQL to create different external views for different groups of software developers. This strategy not only simplifies the software development effort, it also allows the organization to provide data access only on a need-to-know basis for security and privacy purposes. A distributed database is a logically integrated collection of shared data which are physically distributed across a network. Note that this is only a logical integration to give the application developer the impression that they are dealing with a single database system at a single location or in a single database server. This diagram here shows a taxonomy of a distributed database system. First, a distributed database system can be a homogeneous system or a heterogeneous database system. In a homogeneous system, all the local database schemas are the same. In contrast, a heterogeneous system allows different local conceptual schemas. This category of distributed database system is also referred to as a multi-database system. A multi-database system can be federated or unfederated. In an unfederated multi-database system, all users access the system through the global conceptual schema, so there is no local users. In contrast, a federated multi-database system enables local users to access their local database through the local conceptual schema and share their data with global users through the global conceptual schema. And we will discuss all this detail later. There are two categories of federated multi-database system, namely loosely coupled system and tightly coupled system. In a tightly coupled multi-database system, a single global conceptual schema is used by all global users. In contrast, a loosely coupled multi-database system supports different global conceptual schema for different groups of users. So let's discuss the detail of each of the above different architectures. So this is the architecture for a homogeneous distributed database management system. Comparing it to the centralized architecture shown in the lower right, we notice that the homogeneous system kind of resembles the centralized database, but data are now distributed across a number of locations. Global user views are views defined atop the global schema for different user groups. They are similar to the external views in a centralized database. The relation defined in the global schema is fragmented into multiple fragments. The information about these fragments are stored in the fragmentation schema. Location information about where to store each of these fragments is stored in the allocation schema. At each location, the information about its fragments is stored in a local conceptual schema. The file organization, such as indexes for each local fragment, is stored in the local internal schema. This is similar to the internal view of a centralized database management system. As illustrated in this diagram, we can have a hybrid of horizontal fragmentation and vertical fragmentation for a given relation. The relation R has 5 fragments A, B, C, D, and E. First, R is horizontally fragmented into 3 horizontal fragments. The top 2 horizontal fragments are then decomposed into 2 vertical fragments. The fragmentation must make sure that the original relation R can be reconstructed by the relational union and join operation. We will discuss this in more detail later. So this diagram here shows the high-level architecture of a heterogeneous multi-database system. Most homogeneous systems do not have local schemas. Every user uses the global conceptual schema. In other words, there is no local users. In contrast, a multi-database system supports two kinds of users, local users and global user. Global user access databases at multiple locations, whereas local user use only their own local database. There are two categories of multi-database system. Tightly coupled system use global schema, and loosely coupled system do not have a global schema. We will discuss them in more detail in the following slides. This diagram shows the architecture of a tightly coupled multi-database system. At the bottom, the global conceptual schema and the local internal schema are the same as in the homogeneous system. Each location can specify in the local participation schema the portion of the local database as defined on the local conceptual schema can be shared with the global user at the global level. The global conceptual schema is defined in terms of the integration of the local participation schemas from all the database sites. We will discuss this integration techniques later. With the global conceptual schema, different global user views can be defined for different user groups at the global level. Similarly, a local user views can be defined from a local conceptual schema for each database's site or location to support the local users. We note that local user views plus local conceptual view or conceptual schema plus local internal schema at a given site resembles a centralized database management system at this location. The auxiliary schemas describe the rules for mapping between the local and global levels. For instance, rules for unit conversions are necessary if one site expresses distance in miles and another location is in kilometers. We discuss this in more detail in the next 3 slides. In addition to rules for unit conversions, the system may also need rules for handling null values. If one site stores additional information which is not stored at other locations. As an example, one location stores name, home address, and telephone number for each employee, whereas only names and addresses are stored at another location. In this situation, no value would be used for telephone numbers for the latter's location to indicate that the phone number information is not known or not available at this location. Rules for naming conflicts are necessary because different locations may use different names for the same concept or different names for the same concept. As an example, dname and def names are used at 2 different locations to refer to department name. In this case, semantically identical data items are named differently. In another example, Site 1 might refer to department name as name, but name refers to manager name at Site 2. So in this case, 2 semantically different data items are named identically. We also need rules for handling data representation conflict when semantically identical data items are represented differently at different locations. As an example, telephone numbers represented as a character string at one database location may be represented as an integer at another database location. Rules for handling data scaling conflicts are also needed when semantically identical data items in different location data or different local databases use different units of measure. As an example, lot size in United States might be different from lot size in some Asian country. Information on unit conversion is necessary to support global queries that need to access data from both the US database and the Asian database. This diagram illustrates the architecture of a loosely coupled multi-database system. It looks similar to the tightly coupled system with the following difference. There is no global conceptual schema in this architecture. Instead, each of the global user views is defined over one or more local conceptual schema. Missing a global conceptual schema in this architecture for all global users makes this a loosely coupled system. In other words, the local databases are only loosely coupled. In a loosely coupled system, we can also give each location the autonomy to decide what portion of the database to share at the global level. And this is done through the export schema. The export schema is similar to the participation schema in the tightly coupled system, except that multiple export schemas may be defined at each database location. To support processing of global queries in a multi-database system, a global query must be decomposed into local queries, each executed at some local database management systems. Since these local database management systems might support different database models and therefore different query languages, we need query translation to generate these local queries from the global query in the query language at the global level. As an example, we might have two database sites or locations. One uses SQL and another one uses an object-oriented query language. If SQL is supported at the global level, then one of the local query generated from the global query must be translated from SQL to the object-oriented query language before it can be executed by the local database management system. Two translation strategies can be used for these systems. If we want to support all languages at the global levels, then the system requires a translator between every two query languages used in this distributed system. The advantage here is that no global user would need to learn a new query language. However, implementing many translators can be expensive. Alternatively, we can adopt a canonical model, say SQL, at the global level for all global queries. Then we need only one translator from SQL to each of the distinct query language used in the local database systems. This is a less expensive approach, although every global user would need to know SQL. This is not an unreasonable requirement given that SQL is an industry standard nowadays.